Hello, we are going to take a look at some elevator situations, analyzing forces using Newton's second law. So what we're going to do is we're going to look at a person who is in an elevator, and we're kind of imagining that person is standing on a scale. And the reason for that is this. It turns out that scales actually read normal force. And you can think about it this way. If you kind of jump on a scale a little bit, the scale reading goes kind of off the charts. It gets really big or really small, depending on whether you're pushing down or harder or not. And so what the scale is really reading is how much you're pushing on it. And since by Newton's third law, you pushing on the scale is the same as the scale pushing back on you, the scale reading is the normal force on the person. So we're going to be using the scale to imagine the normal force, and then realizing that that normal force is something that we call the apparent weight. So meaning, as normal force changes because you accelerate, your apparent weight gets bigger or smaller. So hopefully that'll become more apparent as we start looking at the examples. So we're going to do 7 scenarios here, and they're outlined here, and then we're going to zoom in on them to take a closer look. We're going to start out at rest, so just looking at the person when they're just at rest. Then we have constant upward velocity, constant downward velocity. We have upward acceleration starting from rest, so speeding up upwards. We have speeding up downwards starting from rest. Then this situation, we were going at a constant velocity up, and then we started to slow down. We are concerned with the slowing down part of the ride. Okay, same idea except downwards here. We were moving downwards at a constant velocity, but then we start to slow down. We're concerned with the slowing down piece. Okay, so those are the scenarios. So now we're going to take a little closer look at the first 3 in particular. So for these 3 scenarios, both at rest is one form of constant velocity. So we could say our velocity equals 0 when we're at rest. And it's a constant 0 velocity. Our velocity is constant here, our velocity is constant here. As a result, for all 3, that means our acceleration is 0. Additionally, when we looked at the balanced force particle model, we noticed that whenever we had constant velocity, it appeared that forces were balanced. And conversely, whenever we had balanced forces, it appeared that velocity was constant. Okay, so here what we've drawn is balanced forces because we know we have a constant velocity. My upward normal force is equal in magnitude to my downward gravitational force. Now remember that gravitational force and weight are the same thing, and we calculate them by taking the mass times 9.8 g. Okay, so now when we add up our forces in the y direction, and now technically we should have a little y underneath this a as well because we're finding the acceleration in the y direction. We add up our forces in the y direction. We can look at this 2 ways. One, when we looked at the balanced force particle model, we said, hey, when forces are balanced, we know that the sum of the forces has to equal 0. So we could just kind of put a 0 there. The other way to think about it is, hey, we've got a 0 acceleration, sum of the forces has to equal ma, so we put in a 0 for a, and we still get a 0 on that right side of the equation. Either way works. When I add up my forces, I have normal force up, I have mg down, and that sums to 0. Therefore, as a result, normal force equals my weight, which is why scales accurately read weight when you're just sitting in the bathroom, standing in the bathroom rather. So the normal force that it's reading is equal to the weight of the person. Okay? If we move at a constant velocity upwards, the same scenario happens. We have sum of the forces equals ma. That term on the right side is 0. So we have normal force up, mg down, and it turns out normal force equals mg. Once again, your normal force is reading, the scale is reading your weight. Okay, accurately. So you feel no difference at a constant velocity as when you're at rest. In fact, if we put you in outer space and we said that you're on an elevator, but it's not going to shudder or anything when it moves, you would have no idea whether you were moving at a constant velocity or whether you were at rest. So situation 3 is just exactly the same thing except for a downward velocity. Acceleration is 0, we have normal force minus the weight equals 0, so normal force equals weight. All 3 of these scenarios, you feel exactly the same weight. Okay? So you feel like you normally would feel as you're walking around. Your apparent weight is equal to your actual weight. So now I'm going to have to look at situation 4, and then we'll have to scroll over to 5 here. So in situation 4, we start at rest. We're going to accelerate upwards. So when we do so, we know that forces have to be unbalanced because forces are only balanced when we're at a constant velocity. We're no longer at a constant velocity. In order to accelerate upwards, there needs to be more force up than there is down. Hence the normal force here, and we can take a little closer look at that. So the normal force here is bigger than the weight downwards. And I've done that because I know that we're going to accelerate upwards. Excuse me. So here I've noted that our acceleration is up, and therefore we've called it a positive acceleration. We generally will say up is positive. We don't have to, it's basically arbitrary, but it makes sense in most scenarios. So when we do our sum of the forces, now we have to leave this ma term over here. We no longer have a 0 over on the right side of the equation. But note that it's a positive term in this case. So we have normal force minus Fg, just like here. We have exactly the same forces, they're just changing their amounts a little bit, equals ma. So when we solve for normal force, we end up with the weight of the person plus another term, this ma term, which means that you feel not only your normal weight, but then an added amount as well. You actually feel heavier. And if you think about it, when an elevator accelerates upwards, you actually, it kind of pushes into you a little bit. It makes you feel a little bit heavier. And so we say that your apparent weight has increased, that apparent weight as measured by the normal force. So now as we go on to 5, 6, and 7, what we've got here, I'm actually going to go over and skip over to 7 for a second because it's similar to 4 that we just looked at. So at 7 we have a constant velocity downwards, but we're going to slow down, and the part that we care about is the fact that we're slowing down. Okay? Now I want you to realize that if we're going downwards but slowing down, we need to have a force that's slowing us down. Something needs to slow us down. And what that means is that our acceleration is upwards. And that's because if we go down and we're slowing down, acceleration has to point the opposite direction of the direction of motion if you're slowing down. We're moving downwards, so acceleration must be upwards. Excuse me, I've caught a bad cold, as you can tell. So our acceleration is up, therefore positive. We still have normal force minus mg over on this side. We still have ma on that side. It's still a positive term. So again, you feel heavier. And if you think about it, when you're going down, but then the elevator slows you down, you feel heavier. So we have normal force equals your weight plus that ma term again. Now 5 and 6 are similar in a different way. So we now have a situation where we're starting out at rest, but we're going to accelerate downwards. And if you think about it, it's kind of like the elevator drops out from underneath you. And so when that happens, first of all, the acceleration being downwards tells us that it's negative. Okay, so I've noted that here. And second of all, for us to be able to accelerate downwards, we have to have an unbalanced force down. So mg must be down. Okay? So now when we do our sum of the forces, we have normal force minus mg, exactly the same, but our ma term is negative because we have a negative acceleration. So then when we add mg to the other side, our weight, we have weight minus ma. So you take your weight here and you subtract a term, meaning you actually feel lighter than you did before. Same idea with number 6 here. If we sum our forces, we have normal minus mg, but we have a down negative acceleration in this case. And let's back up and talk about that for a second. If you're moving up at a constant velocity and you slow down, once again, acceleration has to be the opposite direction of velocity if you're slowing down. So if you're moving upwards but slowing down, that means your acceleration is actually a downward acceleration. So we call it negative. We say this is a negative term here. So we have normal force minus mg. When we add our weight to the other side, we have our weight minus this term. And so again, we feel lighter. And so what I've done over here at the edge is I've graphed the normal force as a function of time. And it's for an object that, it's actually for situation 4 here. So where we started out at rest and we're going to accelerate upwards, but then after accelerating upwards, we're going to then go into this situation. So we're going to then slow down. So it's a normal elevator ride going up a story, for example. So when you speed up at the beginning, your apparent weight is slightly higher than your actual weight. When you're going at a constant velocity here, your apparent weight is equal to your actual weight. And when you're slowing down at the end but you're moving upwards, then your apparent weight is less than your actual weight. And so that's just one situation. If you went down, so if you went down a floor, this would be exactly the opposite. You'd have a lower apparent weight as you sped up downwards to begin with. Then you'd have, again, constant velocity would be apparent weight equal to actual weight. And last of all, when you did your slowing down while moving down, your acceleration would be upwards. You would have a higher apparent weight. So that's a summary overall of the 7 different situations that elevators can kind of possibly be in, and using Newton's law to analyze what your apparent weight is doing.